I went over to Desmos and plotted 8 points, and here they are. And these points all have something in common. They all are the same distance from the origin, from 0, 0, the point 0, 0. And when we say the origin, usually we're talking about on the xy plane, the point 0, 0. X is 0, y is 0. So all of these points are the same distance from the origin. In other words, we could think of the origin as a center point. And these points, if, I only plotted 8 here, but if I plotted more that were the same distance from the center point, we would have ourselves a circle on our hands. And in fact, well, it'd start to form a circle. If we took all of the points that were equal distance from the center point, the way these are, we would have a circle. Now, the distance I'm talking about is one unit. So if we talk about all the points that are 1 unit from the origin, then we have a circle, and that particular circle is called a unit circle. It's a circle of radius 1. Now, if we had a circle of radius 2, then that would refer to all the points in the plane that are 2 units from the origin. Or it doesn't have to be the origin. It doesn't have to be 0, 0. If we take all the points that are equal distance from a center point, just in general, like that, we refer to that as a circle. It's the union of all points that are equal distance from a center point. And this point, in this circle over here, the center happens to be 2, 1. Okay, and let me label it here. 2, 1. There it goes. And we can move this circle up and down. See, there's up and down. We can move it left and right. Let me zoom out a little bit here. I can move it left and right. And I can just, I can just move it around. Each component of the circle I can move around. Okay, there it goes. That circle is just moving around. And that circle, so here's what happens with this circle. Let me pause it. What happens with that circle is, this circle is of radius 1. This circle that we were moving around is of radius 1. But all I've done is I've taken that circle that was centered at the origin, just moved it. Now, how did I move that circle around? Well, I didn't just say x squared, I said x squared, I said x minus something, all that squared. In other words, that something is how far we move it to the left and right. Notice here I've got h. See, you can see h, and I can move it. That's a horizontal motion. It's in there with the horizontal component, x, and it moves it to the left and right. The component here with the k here with the y, that moves it up and down. See? As I move this slider up and down, we get the circle that moves up and down. And if I put them together, they move it left and right, up and down, and so forth. But this is how we, first of all, it's how we define a circle. It's the union of all points equal distance from a center point. And then how we move that circle around, well, we change the what's in there being squared with the x and what's in there being squared with the y. Okay? Now, let me, one more thing before I do this. Notice I can make the circle bigger too. So let me just pause this where it is. If I increase the radius, maybe I'll go back and make this a radius, increase it a little bit. See? Maybe increase it a little more. Maybe make that a 9 over there. See, I can increase the radius or I can shrink it back down to the unit circle, okay, like it was. But, so we're going to explore that a little bit. Now, first of all, let's just go back and look at a circle. Let's suppose that we've got a circle here and it's centered at some point, I'll call it HK. Now, this xy right here, this point up here, is just some point on the circle. In other words, this point is a radius distance from the center. Okay, the distance this point is from the center of the circle, we call that r. That's some number. That's the radius. Now, how do we find distance? Well, we use the distance formula. Remember, you take, or really, you're using Pythagorean theorem. Notice that I've got this distance here, which is the hypotenuse of a triangle. Okay, here's the horizontal distance. Here's the vertical distance. See, I get the horizontal by saying, okay, the difference of the x's, x minus x, or x minus h. The difference of the y's, I got y minus k, see? So I've got this side of the triangle, this side of the triangle, and then I've got the hypotenuse. Well, you know, I could call this side delta x, you know, that distance. I could call this side delta y. We've dealt with that before. And I could just say, well, the distance squared is c squared, or in this case, r squared, equals a squared plus b squared. See? C squared equals a squared plus b squared, but this is playing the role of a, this is playing the role of b, and this is playing the role of c. So you can see here that we get the formula, an algebraic expression for this circle. A circle of radius r that's centered at hk. And dig this, here's the center, hk, the radius is r. So, for example, let's suppose that we have this circle, okay? This is just a representation of Pythagorean theorem. And you can immediately see what the center is because, you know, normally we have a circle centered at the origin. Well, this one's not. It's been scooted over 3 units. So you could think of this as a shift. But you're just using Pythagorean theorem, but it has a cool property that what we have here is this whole triangle has been shifted to the right 3 units. Okay? And it's been shifted up 4 units. Okay? So it's been shifted because look, that may be counterintuitive to you, but notice in this case, h was 3 and k was 4. So we did h minus 3, y minus 4. So 3 and 4 started out being positive. So the center is 3, 4. It's the opposite of what's in there. And then the radius is just the square root of this little fella right here. Yeah. So the radius is 5. So if you see this, look at this. We want to know, okay, what is the center of that circle? Well, we get the x-coordinate from the parentheses with the x, but it's the opposite. We get the y-coordinate from the parentheses with the y, but it's the opposite. So this one has a center of negative 7, 5, and the radius is the square root of whatever this is, which we could just write it as the square root of 2. Okay, so whenever we have something that looks like this, we can immediately know, okay, that's a circle of radius hk and a radius of r. Now, let's suppose that we don't have something cool like this. Let's suppose we have this. And we suspect this is a circle because it's still got the x squared and the y squared in it. So we're suspecting that's a circle, but we would like to know what the center of that circle is. And we would like for it to be more like this form right here, where we could just read the center, HK. Well, I can't do that here. But look at this. I want to show you an algebraic manipulation that we can use. Let's suppose I wanted to take this expression and rewrite it. Well, let me just take this expression, this one right here, and I'll just put a little rectangle around it. Okay, I'm going to look at that geometrically. In other words, I'm going to look at this as an expression of area. For example, x, I'm going to look upon that as an x by x square. See, it's x squared. What if this side is x units long and this side is x units long? Then this area in here is x squared. What about these 6x's? Well, let's take an x unit long and a 1 unit wide rectangle. If this is x units long and 1 unit wide, this area in here would be x. And let me do this. Let me take half of them and put them here, and half of them put them over here. See, I'm taking half of this 6. Here's x plus x plus x. That's 3x. X plus x plus x. 3 more x. 1, 2, 3, 4, 5, 6. 6x. So the whole area of this thing is x squared plus 6x. In other words, it's this. Now, this is not what we would call a perfect square because we've got this big gap here. Now, I can fix that gap by sliding this over. See? Right now, I don't have a perfect square. But look at this. Here are 9 1-by-1 squares, and I will just slide it over here in this gap. And now notice, this makes a perfect square. Okay? The imperfection there is in my drawing, but you see now we've got, up top, we've got this side here is x plus 3. See, that length there. We've got x and then 1, 2, 3. And then this side over here, this side is also x plus 3. So if I were to ask you the area, you would say, well, x plus 3 times x plus 3. Or you could just write that as x plus 3 squared. Notice it's x and what? This, which is half of the 6. So I could immediately, so in other words, notice what I did there. I added the 9, okay? So here's what happens. I had x squared plus 6x. And I added a 9 to it. Now, when I added a 9 to it, what I did was add this. I now have something that could be factored as x plus 3 times x plus 3. In other words, I have now something x plus 3 squared. So let's look at this. Let's rewrite this one. I've got x squared plus 6x. I need to add a plus 9 onto that. Now, I can't just add a plus 9 to one side and not the other. You know, I've got to keep it balanced. Okay? So let me see what I've got here. Over here, I've got 0. Now I'm going to do a plus 9. Okay? Now let's see what happens. Now I've got a plus y squared plus 8y. Okay, I need to add something there. I think what I'll add there is half of the 8 squared. Yeah. See? So what I'm doing is I'm taking half of the y term, squaring it, and now what I've got is I've got a new way to look at the circle. I've got the x squared plus 6x plus 9. I can write that as x plus 3 squared. All of that, all of this, I write this way. Okay? Now, plus y plus 4 squared equals 25. Okay? This is y plus 4 squared. And that is, of course, this. So now you can easily see what the center of that circle is. It's -3, -4, and the radius is the square root of 25, which is 5. Yeah, that's it. Okay, so remember, what we do is we take half of that, square it, add it over here, half of this, square it, add it over here, and now rewrite x and this thing squared plus y and this thing squared equals 25. Yeah, that's how we do it. Now, let's try it. Let's try it over here. Here I've got this circle. The first thing I want to do is I want to rewrite it, making sure my x's are together and making sure my y's are together. And I move everything else to the other side. So this is 2 minus 2 plus 3. Okay? And let me scoot this over a little bit. I didn't give myself much room here. Okay. Move this over. Okay. Okay, now. So here's what I've got. And so I moved everything that's not an x and a y to the other side. I subtracted 2. See, there's that. And I added 3. Now, let's do our work here. I'm going to take half of this and get negative 2 and square it, and I get a plus 4. So I need to add a plus 4 over here as well. Now over here, I take half of the y, square it, add a 9, add a 9 over here. Now let's see what I've got left. I've got x minus 2 squared plus y plus 3 squared equals, let's see what this is. This is going to be 9 and 4, that's 13, 14, 15, 16. There we go. Okay, now we have the center, which is going to be 2, negative 3, and the radius, which is going to be 4. And there you have your circle. A circle that's centered at 2, negative 3, and a radius of 4. And this is called the completing the square method. Now, that's a good thing, a good skill to have, completing the square, because you see this over and over. You'll see it in college algebra, trigonometry, calculus 1, 2, and 3. Completing the square pops up all the time. So you want to be familiar with that technique. Now, when we talk about 3 dimensions, we might as well talk about spheres. Since we're talking about completing the square and circles, let's just throw in the spheres. The difference is you've got the z component. So if you have something like this, something like this right here, you've got your center of the sphere. Now, a sphere is all the points equal distance from a center point. But there's a x, y, and z component. So this one's going to be 2, negative 4, and 5. That's the center of this sphere. The radius, it's still going to be the square root of what's on the other side. Okay, so this is something, not a lot changes. You're still using the Pythagorean theorem, but it's a little more involved to see, but it's still the same principle. Okay, so let's see how this works. Okay, I've got a sphere here, and I'm thinking it's a sphere because it's an x squared, a y squared, and a z squared. Okay, so let's see how this works. I'm going to group my x's together. Okay, I'm going to group my y's together. I'm going to group my z's together. And I've already got a 2 over there. I'm moving a 1 over, and that's it. Yeah, there it goes. So I grouped all my x's and y's and z's together. And anything that's not an x, y, or z, I move to the other side. In that case, it's just this 1. Okay. Now, let's commence to completing the square. Here I go. I'm going to take half of the 8 and square it. You get 16. I add a 16 over here. Now I'm going to take half of the y, square it, and I add a 1 over here. Now I'm going to take half of this, -3, square it, you get a 9. I'll add a 9 over here. Notice every time I just took half of the linear term and squared it. Okay, so now let's see what I have over here. I've got x plus 4 squared plus y plus 1 squared plus z, minus 3 squared equals, let's see what's going on over here. I've got 1 plus 16, that's 17, 18. I guess is that going to be 27? I think it's going to be 27. I think so. Let's see here, 9, 10, 26. Yeah, 27. There we go. Okay. So now here's what we got. We got the center, which is -4, -1, and 3. And we got the radius, which is the square root of 27. And you could simplify that if you wanted, that radical a little bit. It's got a 9 in there, but I just leave it as the square root of 27. Okay, so there is how we're going to, that's the process that we're going to use to find the center and the radius of circles and spheres.